سعيد إن شاء الله. My name is Mandar Alhamdi. I'm an adult cardiologist, electrophysiologist at King Faisal. And today actually I'll start with you something you know already from before. I'm just going to review with you the basics of ECG. You have it before in phase 2, but we'll go over it quickly, and then the next few lectures will be about the clinical applications of the ECG. So let's start with items. Today we will look at what is ECG, number one. Why do we need ECG? The ECG leads, and then basics of ECG interpretation, heart rate, regularity, rhythm, and axis. So can somebody tell me what is ECG? What is electrocardiogram? Good. Yeah. Okay, so we close this. What is electrocardiogram? Basically is a graphic representation of the cardiac electrical activity. So we know that what we see by our eyes is muscle contraction and relaxation. What is behind that relaxation, the contraction and relaxation, is depolarization and repolarization in the myocardial cells. Okay, and this thing, if you detect it with electrodes in the chest and in the limbs, we call it ECG. So again, it is a graphic representation of the heart electrical activity. So the electrical activity in the heart produced by the pacemaker of the heart, which is the sinus node, and also the conduction system, and the myocardial cells in the atrium and in the ventricle. So remember, when the sinus node fires, we have action potential in the sinus node, and this is spread from cell to cell. So we have activation in the sinus node area. We see nothing in the ECG. Why? Because this is small tissue, and the electricity is small. So when we put electrodes outside the body, we cannot detect that electricity. However, when it spreads to activate the right atrium and the left atrium, then we see P wave. So a P wave is atrial depolarization. It is larger tissue, larger muscle, so we can see more of activation, and then we start to see the P wave. When it goes down the AB node, bundles and Purkinje fibers, it is PR segment. There is no electricity, but there is conduction. But we cannot detect anything externally. When the ventricle depolarizes, we have the QRS complex, and then we have the P wave. So ECG is not action potential, but it's summation of all action potentials in the atrium and in the ventricle. So this is how it's been done. As you know, we have electrodes in the chest, electrodes in the limbs, connected to a machine, and from the machine it printed out the waveform that we have from the heart. So always put that concept in your mind. We have electricity in the heart, we are measuring them by electrodes on the chest and on the limbs, and we look to different waveforms, and we have normal and then abnormal. We'll go today over the normal, and then we'll discuss the abnormal later on. So why do we need ECG? Why we are doing it, and why it's important for everybody, even not a cardiologist, to know the ECG? Why? What is the importance of ECG? What's that one? For diagnosis of what? For arrhythmia. So the number one arrhythmia, why? Because if the heart rate is 150 beats per minute, we can calculate it by we can get it by pulse oximetry. But it could be sinus tachycardia, could be atrial tachycardia, could be atrial fibrillation, could be a ventricular tachycardia. We know the source by looking to the ECG and the waveform of the ECG. Second, remember when we manage acute coronary syndrome, it's very common. Myocardial infarction is very common. We did classify them into ST segment elevation and non-ST segment elevation based on the ECG at the beginning. So we start screening them based on the ECG. If there's ST segment elevation, we're dealing with ST segment elevation. We manage differently from non-ST segment elevation myocardial infarction. So that is very important. If there is conduction problems, first degree, second degree, third degree, how to know? By looking at the ECG. We cannot diagnose it by any other modalities. If there is ventricular hypertrophy or atrophy, ECG is important diagnostic tool, then we go for more specific like echocardiogram to look for the hypertrophy or atrophy. Others like medication effects and others. So there are many diagnoses that we can get from the ECG. Okay. Let's go to the basics of the ECG. So this is the line in the ECG machine. The isoelectric line we call it, so zero activation in that line. Above it, or positive wave is called, this part is positive. Upward or positive. So anything above the baseline is positive or upward activity. Anything below it is negative. So in this case, the P wave, the R wave in the QRS complex is positive because it's above the line. The S wave is negative because it is below the baseline. T wave in this example is positive, but if the T wave is inverted, then we are dealing with negative T wave. So anything above the baseline or upward deflection is positive, anything below the baseline is negative. Second important thing, I showed you that electrode we placed in the chest. There are positive and there are negative electrodes. Always we concentrate on the positive electrode. Okay, sorry, I just take this because it's easy to pull. So if activity of depolarization or the wave of depolarization is moving towards the positive electrode, it will produce positive deflection. So it is above the line. If it is moving away from the positive electrode, it will produce negative deflection. So this is what the price now. Okay. What if it's perpendicular? So it moves, the wave of depolarization is moving this way. So it comes to the positive electrode, there is positive activity. It also comes to the negative electrode, we have negative. And if it is really perpendicular, that positive and negative will be equal and they will cancel each other as if there is no activity. So now look to this ECG electrode placed in different part of the chest. So this is the electrode. And this is the wave of depolarization. The net activity is going this way. So this electrode will be positive or negative? Positive and all positive because everything is coming toward this positive electrode, so I have positive deflection. Opposite is this electrode. The wave of depolarization moving away from it, so it will be negative deflection. The one which is perpendicular have positive, negative, they are equal, they cancel each other as if there is nothing there. How about this one? Will it be more negative or positive?
More negative.
Okay, it's moving mainly away, but there's something coming towards it. So R, or the positive part is small and the negative is more. The opposite to this one, it's mostly towards this one, so I have more positive than negative. And this is the same for ECG when we place in the chest, and we will see the waveforms in different ways. It depends on this concept. Okay. Amplitude of the waveforms. So tall, short, it depends on the muscle. So if somebody has hypertrophy, you expect the signal will be bigger or smaller?
Bigger.
Bigger. With hypertrophy, there is more mass, more electricity, and then bigger wave. Somebody has myocardial infarction and lost part of the myocardium, the signal will be small. So we may not keep the signal. The net vector of depolarization, if it's going toward that electrode, it will be more positive. If it's moving a little bit away from it, the R wave will be smaller and smaller. If it moves totally away from it, it will be totally negative. So the net vector of depolarization is important. And the intervening tissues, the conduction is different from. So actually, you see, when we do the ECG, always we try to shape the chest because if there is here, you cannot get good conduction. So the tissue between the electrodes and the body is important. The distance between the electrode and the myocardium is important. So if somebody is obese, you expect signal to be smaller or bigger?
Smaller.
Smaller, because there is more distance between the electrode and the heart. If somebody has precordial effusion, smaller or bigger? Smaller, because we are separated from the heart by the effusion itself. The same for emphysema. Emphysema, inflation of the lungs. It moves the heart away from the electrodes, so again we will see smaller signal in the right side. So that is a few things about the basic concepts. We know that the heart is three-dimensional structure. So if I'm looking only one direction, I may not see electricity. It does not mean that there is no electricity produced, but maybe it is in another direction. I don't see it. So at least we need two planes to look to the heart. We have the frontal plane and we have the horizontal plane. And we will talk to them now in a minute. So limb leads is looking to the frontal plane. The chest lead looking to the horizontal plane. And we'll discuss them in a minute. You'll know. So remember the 12 leads? So what are the limb leads? 1, 2, and 3. And we have augmented vector right, augmented vector left, and augmented vector foot. These three and these three, the 6 of them, we call it limb leads. These are the leads that look into the frontal plane of the heart. Chest leads, V1 to V6, and it looks to the horizontal plane of the heart. We'll take them, let's take them one by one. And remember, the most important for us is where is the positive electrode, where is the negative electrode. So lead 1, we place the negative electrode in the right arm and the positive in the left arm. So we measure the difference between these two electrodes. So what do you expect lead 1? Will be positive or negative? Let's talk about the P wave initially. P wave will be negative or positive in lead 1?
Positive.
Why? Because activation of the heart starts from the sinus node this way. So it is downward and right to left. So it's moving towards lead 1. So I expect P wave to be positive. Excellent. And how about QRS complex? Again, the same thing.
Positive.
Activity of the heart, the main vector of depolarization is going this way, so it is towards lead 1, so I have positive QRS complex in lead 1. Okay. Lead 2, I have the negative electrode here in the right arm, I have the positive in the front. So the positive electrode is here. So would you expect the P wave to be positive or negative? Positive again. QRS complex? Again, positive, excellent. How about lead 3? There is the negative electrode and the positive electrode, so it is actually a little bit closer to lead 2. But there is a little difference, we'll discuss it in a minute. So you expect P wave to be positive and QRS complex to be positive in lead 3. Any questions? The positive electrode. This is standard, you know. So always when we place an ECG, we put the negative electrode here, we put the positive electrode here, and this is lead 1. So if somebody misplaced them, by the way, we commonly see it an error in ECG, we call it limb lead reversal, and the machine actually will start to give you limb lead reversal because this is the standard. So the standard way we put positive electrode for lead 1 here, positive electrode for lead 2 and lead 3 in the front. That? Yeah, P wave, why it is positive? Because remember the atrial activation is going from the sinus node, which is the junction at the SVC. It goes from up, down, and from right to left. So up, down, the inferior release will be positive. The P wave should be positive in inferior. Of course, because the atrial tissue is small compared to the ventricular tissue, the P wave is very small compared to the QRS complex. Right? Oh. The augmented leads actually is similar, but why I said, okay, this electrode in the right arm, why not to use it and measure it as a positive electrode? But where's the negative electrode? It's calculated by the machine in the center of the heart. So this is called unipolar. Why? Because the only electrode we are using is the one in the chest. The other electrode is indifferent electrode, we call it, is calculated by the machine as if it is in the center of the heart. Not real electrode like the other bipolar lead. The two leads I showed you, there is real negative electrode, positive electrode. In this one, I have only one electrode. The other one is calculated by the machine in the center of the heart. So that's why we call it unipolar. And why we call it augmented? The signal is very small. So the machine has to increase it, augment it for us so we can see it. So it's called augmented. So if the electrode in the right arm, we call it augmented vector right. What do you expect P wave in the augmented vector right? Will it be positive or negative?
Negative.
Negative, because everything is moving away from atrial activation. QRS complex would be also negative because it's moving away from it. Left arm, if I put the electrode there and I said, okay, this is my augmented vector left in the left arm. So it is the same as lead 1. So P wave is positive, QRS complex is positive. The augmented vector foot is similar to lead 2 and lead 3. Okay? Because the positive electrode is in the lower. If I join these 3 true bipolar with the 3 augmented vectors, which is unipolar, we have the 6 limb leads. The 6 limb leads. And these 6 limb leads looking to the frontal plane of the heart. This may look a little bit hazy there, but and you have this in physiology before. So this is lead 1, this is lead 2, and this is lead 3. It's called inferior triangle. This is a triangle. So if we wanted to take this to the center of the heart, and sorry, just by mistake. Okay, let me try to explain it. Although it's very hazy, sorry. But if we wanted to bring this to the center of the heart, we will have lead 1, we will have lead 2, and we will have lead 3 this way. Just imagine that we bring them together to the center of the heart. And by convention, we say lead 1 is 0. Other leads is related to lead 1. Lead 1 is 0, other leads related to it. So lead 2 will be 60 degrees, and lead 3 is 120. If we take the augmented vectors, I know it is very hazy there, but you can see it on the PowerPoint presentation. And we do the same, we bring them in the center of the heart. We will have augmented vector left, right, and foot. And when we join the together, the 6 limb leads together, we will have the complete circuit. And we will come to it in a minute. But this is how the way it's been done. We know each one is triangle. We just bring the leads to the center of the heart, and we have different orientation for lead 1, 2, and 3 for augmented AVL, AVF, and AVR. Chest lead is much easier. Chest lead, we place them on the chest, but it's important to recognize the location. So V1 in the fourth intercostal space to the right. So we calculate second, third, and fourth, and we put it fourth just to the right of the sternum. 2 is the opposite. So in the left side, but it's in the fourth intercostal space. The fourth in the fifth intercostal space, so we move one space in the mid-clavicular line. So this is the clavicle. In the mid-clavicular line, we have B4. 3 is between. So 3 is different from person to person, but it's in 5 and 6, we just go to the same fifth intercostal space, but in anterior axillary line and mid-axillary line. So this is the standard. And we have one electrode here. So it's only unipolar leads. The second electrode is calculated by the machine, the same as augmented lead in the center of the heart. So basically, we have bipolar lead 1, 2, and 3, unipolar augmented lead, and the chest lead all unipolar. One electrode, and the other one is calculated by the machine in the center of the heart. Now let's look to what we expect the signal to be. So lead 1, we mentioned P wave positive, Keras complex positive, T wave is positive. Lead 2, the same, lead 3 is the same. Why lead 2 is taller R wave than lead 3? Yeah, the wave of depolarization more towards lead 2. It goes this way, more towards lead 2 than lead 3. So we have it more positive in lead 2. Right? This is the basic principle. Wave, the waveform it's more towards the positive electrode, more positive. Away from the positive electrode, less negative. But I'll show you in a minute. This is lead 2. It goes more towards lead 2 than lead 3. So lead 2 would be more positive than lead 3. Okay. And for AVR, we mentioned all negative because it is here and everything is moving away from lead AVR, so it is negative. AVL is closer to lead 1, so positive P wave, positive Keras complex, and the AVF close to lead 2 and lead 3, so positive P wave and Keras complex. This is the normal, because later on when we get abnormal, then you will explain okay, where is the abnormality. This is just to remember, overall direction of activity of the heart is towards actually 60 degrees. This is the normal. However, it is between minus 30 to 90, and we will discuss it in the axis in a minute. For V1 to V3, let's look to lead V1. It is in the fourth intercostal space to the right. So, what do you expect P wave to be? Positive, negative, or biphasic? And why? Could be negative, or positive, or actually biphasic. The commonest is this morphology you see. There is a small positive followed by small negative. Why small positive? Right atrial activation. Remember, the right atrium is like this. The sinus node is here posterior. So activate the right atrium. It goes towards V1. V1 is anterior of the chest. So V1 anterior of the chest. So activity of the right atrium is going towards V1. So I have small positive P wave. When it activates the left atrium, is moving away from V1, so I have negative deflections. That's second part. So actually, most of the time, commonly we see P wave in V1, positive then negative. Positive right atrial activation, negative left atrial activation. And it is small like this, not huge. When it is big, we will discuss left atrial enlargement and others, inshallah, the third year. What do you expect our wave? Will it be positive or negative? Remember, activity of the heart is this way.
So positive.
Okay, it is mostly negative. It's mainly moving away from it. So I have small R wave, which is the small positivity, but it's actually mainly moving away from it, so more S wave than R wave. V2, you expect R wave to be bigger or smaller than V1? Bigger, because it's more of wave depolarization going to V2. 3, even bigger. 4, bigger. 5, the largest R wave usually in V5. V6, because it's a little bit lateral, so generally V6 is a little bit smaller than V5. This is called R wave progression. You expect R wave to be bigger with time in the chest. This is normal, just because of the activation is going this direction. So I have very small R wave in V1, bigger in V2, bigger in V3, 4, and 5, the maximum in V5, and then a little bit less in V6 because the V6 is more lateral than V5. Okay? Clear for everybody? This is called normal R wave progression. Go ahead. You see, P1 in V1 can be negative, which is the wave of depolarization is opposite the same. So normally it can be biphasic or negative in V1. This is the normal repolarization wave in V1 is negative. We try to always look about depolarization because the depolarization is very variable. So we don't usually discuss the T wave, except in ischemia we'll discuss it later, it depends on the location. But normally T wave can be negative in V1, sometimes actually up to V3 in young people, and when we get in the adulthood, only V2, V1 can be negative, others can be positive. So there's changes with the age. Okay. Let's look now to V1, V2 and the heart. Which area of the heart they are looking to? Which area?
Right.
It is mainly looking to the right ventricle and the septal area. So if you think it, usually we see V1, 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 V2 is septal area. 3 and 4, anterior surface of the heart. 5 and 6, lateral areas of the heart. I go back just to show you again the same thing for the inferior. Lead 2 and 3 looking to the inferior surface of the heart. AVF also looking to the inferior surface, we call it inferior lead. It looks to the inferior surface of the heart. AVL, lead 1, looking to the lateral surface of the heart. Right? So, we know that P wave is atrial depolarization. PR is the conduction down the AV node conduction. QRS complex is the depolarization of the ventricle. Just a cartoon just showing the same thing. So, when the sinus node fires, anything in the ECG? Just sinus node activated. No, because the activity is small, we cannot detect it by electrodes outside the body. Yes? Okay. When the atria activated, depolarized, what we see? P wave, excellent. So when it goes down the AV node, the bundles, the Purkinje fibers, anything in the ECG? It's conducting, but there's no electricity we detect outside, so it's baseline, the PR segment. When the ventricle depolarized, what we see? QRS complex, excellent. And then when it repolarized, we see the T wave. So this is what is happening all with each beat. Activity spreads, and then mechanical activity following that. Atrial contraction, ventricular contraction, atrial contraction following. So the ECG is just recording what is happening on a daily basis with each beat. The layout of the 12-lead ECG, most of the hospitals use this format. So we have the limb leads, the 6 of them, and the 6 chest or precordial leads. Bipolar, lead 1, 2, 3, augmented, AVR, AVL, AVF, V1 to V3, V4 to V6, and we have what we call rhythm strip. We'll come to it in a minute. So this is most of the time, you look to the lead ECG, in most of the hospitals, this is the layout. This is the limb leads, chest leads. 1, 2, 3, AVR, AVL, AVF, V1, V3, V4, and V6. So with time, you get used to, or once you see something abnormal, you can discover it from the beginning because there's something deviated from the normal. Rhythm strip, as you see, will continuously record because ECG is about 10 seconds. And this is only recording lead 2 for 10 seconds. We can't calculate the heart rate, we look to the rhythm from lead 2. In other leads, it's only 2 beats, for example. I cannot be sure it's regular, it is irregular. How to calculate the heart rate, I cannot be accurate, but when we have this rhythm strip, can be 1, can be 2, can be 3. In our hospital, usually we have actually lead 2, V5, and lead 3 as continuous rhythm strips in the bottom of the ECG. In other hospitals, what they do, they put the limb leads here, 6, so we have 1, 2, 3, then AVR, AVL, AVF on one side, V1 to V6 on the other side. So once you see the ECG, just familiarize yourself. Is it this format or that format? This is the common format. Oh. When we record the ECG by old machines, there's a stylus like this, and the stylus, we move the paper and the stylus moves to give us the form. So the speed of the paper is important, and that's actually what gives us the time. And the voltage, which is how far this signal is in the horizontal, in the vertical there. So horizontal is the time, vertical is the voltage. And the standard is 25 millimeter per second. The paper is moved 2.5 centimeter per second, 25 millimeter per second. This is standard. So, and when it moves this way, the paper grids, small square will be 40 milliseconds, which is 0.4 of a second. Large box will be 0.2 of a second, which is 200 milliseconds. So in that case, how many in a second? Large boxes? 5. 1, 2, 3, 4, and 5. So just again, this is speed, which is 25 millimeter per second. Each small square in the ECG paper will be 40 milliseconds, or 0.4 of a second. Each large box is 0.2 of a second, or 200 milliseconds. So it means for 1 second I have 5 large boxes. Okay? For the vertical, it is calibrated that that stylus will move 2 large boxes for each 1 millivolt. So when there is 1 millivolt, it moves 2 large boxes. So each small square will be 0.1 millivolt. So this is for the time, and this is for the voltage. Remember, each small square is 40 milliseconds. Each large box or large small square is 200 milliseconds or 0.4 a second. Now let's look to the signal itself. We'll take this signal from the beginning to the end. So first part is isoelectric. What does it mean? Isoelectric? There's no electrical activity, right? Okay. Then followed by P wave. What does it represent? Atrial depolarization. Right and left atrial depolarization together. We have a P wave, and this is lead 2. So we expect the P wave to be positive. The duration and height is important. We will discuss it on the third wave. Left atrial abnormalities, right atrial abnormalities, because P wave represents atrial depolarization. If there is hypertrophy or enlargement of the right or left atrium, we'll see changes in the P wave as well. So normally it's 2.5 by 2.5, the height and width. Okay. Then we have the PR interval. That's the conduction down the AV node and his Purkinje. It's isoelectric because it's just conducting, but we don't detect anything externally. When the ventricle depolarizes, we have QRS, the QRS. Q by definition, first negative deflection after the PR segment, and after the P wave. R is the first positive deflection. S is the first negative deflection following the R wave. Not every time we'll have QRS complex. So most of the time we may have just only R. We still call it QRS complex, but the Q and the S is not there, so it is only R, but we call it QRS complex. Sometimes it could be all negative, we call it QS. It depends on the location, it depends on the anatomy. So not necessarily you will see QRS in each signal. And you will see most of our signal, there is no Q wave, for example. Q wave only for lateral lead for septal activation. You don't see it all the time. Okay. Then we have the ST segment, represent plateau phase of action potential. ST segment, and this is actually important for ischemia and infarction. We'll discuss the ST segment, very important for ischemia and infarction. When there is repolarization, we have the T wave is for ventricular repolarization. The QT interval is from the beginning of the QRS complex, so Q comes from QRS complex, and end of the T wave, so that's why we call it QT interval. It is the time for ventricular depolarization and repolarization. Abnormalities in the QT interval can produce arrhythmia. We'll discuss them also in arrhythmia part, inshallah, later. So basically, typical ECG will look like this. We'll have a P wave, we have PR segment, QRS complex, T wave, and then continuously recording at the same time. And the normal PR interval, there is normal, so lower limit and upper limit. Try to remember it in small squares. So PR, which is from the beginning of the P wave to the beginning of QRS complex, it's between 3 to 5 small squares. 3 means 120 milliseconds, which each one is 40. 5, it means 200 milliseconds. So between that range, if it is shorter, it's abnormal. If it is longer, it's abnormal. QRS complex is 1.5 to 2.5, so 60 to 100 milliseconds. Generally, we rarely see something narrower than 60, but it could be wider. And if it is wider, it means conduction is taking longer time, so it's wider QRS complex, like in bundle branch block we will discuss inshallah later. For QT interval, the norm, the beginning of Q till the end of the T wave, this is between 360 and 440 milliseconds. There is short QT syndrome and there is long QT syndrome. Again, we'll discuss it with the arrhythmia inshallah. So now how to analyze ECG. When you have ECG in hand, the first thing to make sure is that ECG belongs to the patient you are looking at, because sometimes the ECG could be misplaced, or somebody entered the wrong number, for example, medical record number. So always try to make sure the name and medical record number is for the same patient, because otherwise, for example, it's atrial fibrillation, you start managing patient atrial fibrillation, actually the ECG is for somebody else. It will be managing the patient, mismanagement of the patient. So make sure this belongs to the same patient by 2 identification, usually name and medical record number. Second, make sure calibration is right. So the speed is written down, actually 25 millimeter per second, and the voltage. It should be 1 millivolt equals 10 small squares. Okay? Then you go to rate, rhythm, regularity, the conduction part, the PR, QRS complex, the QT, the axis, we'll discuss it in a minute. We look to the POA morphology, is normal or abnormal, QRS complex, ST segment, and then to reach final conclusion. Is normal sinus rhythm with no abnormalities, or sinus rhythm with ST segment elevation, for example, inferior MI, or ST segment elevation, anterior MI, depends on all of this. So with time, inshallah, you will see we will come, by end of all the ECG lectures, at least you will have the more common diagnoses that you can reach, inshallah. So look to the rhythm analysis. How to calculate the heart rate, by the way? How can we calculate the heart rate? Yeah, from the ECG. Yeah, excellent. So RR, how many large boxes, and 300 by that. Why 300? So remember, in 1 second we see we have 5 large boxes, yes? In 1 second. So in 60 seconds, 5 by 60 is 300. So in 1 minute we expect to see 300 large boxes, yes? In 1 minute. So we see how many cards complex in that one. Each card complex is 1/2 p, right? So we divide 300 by the number of large boxes, it gives you the heart rate. If it is a small boxes, what to use? 1,500. So just multiply, because each large box is 5 small squares. So multiplied by 300 by 5 is 1,500 divided by number of small squares. So that's the rate. I'll show you actually example of it. Regularity, you look to the RR. Is it regular or irregular? Then at P wave, is it upright or not in lead 2? In this case, it is upright, so it is normal P wave axis. The PR interval, is it normal or long? Remember, 3 to 5 small squares, the normal PR. Shorter than that is abnormal, longer than that is abnormal. We'll discuss these abnormalities. QRS complex morphology and duration, and then determine the axis. So for heart rate, as mentioned, the number of, so for example, if I take this patient, and between this R to R is 1, 2, 3, 4, 5 large boxes. So what is the heart rate? 300 by 5 is 60 beats per minute, right? And for easiest, usually when you see that between R to R is 1 large box, 300 beats per minute. This is pathologic, of course. Most of the time we see it in ventricular tachycardia. We can see 2 R's. The distance between the two is only one large box, so the rate is 300 beats per minute. If it is 2, 300 by 2, or 50 beats per minute. If it is 3, 300 by 3 is 100 beats per minute. If it is 4, 75, because 300 by 4 is 75 beats per minute. If it is 5, 60 beats per minute. If it is 6, 50 beats per minute. So easiest way is just number of large boxes divided by the 300 divided by the number of large boxes between the RR. So this has to be a regular rhythm. If it is irregular, how to calculate the heart rate? So suppose somebody with atrial fibrillation, RR is very changing. So how to calculate the heart rate in that case? The best way is to take the ECG usually is 10 seconds. So take 10 seconds, see how many QRS complexes in that 10 seconds. So if, for example, 1, 2, 3, 4, 5, 6 in 10 seconds. So in 1 minute, how many? I multiply by 6, right? Because I want 1 minute, I have only 10 seconds. I want 1 minute. So you look to the RR interval. Like this case, for example, RR is totally irregular. It is continuous. This is just an example to show you the calculation of the rate side. Suppose this is for a patient and the RR is very variable. We take 10 seconds. How many QRS complexes? This is the heart rate in 10 seconds. I multiply by 6 to bring me 1 minute. Clear for everybody?
Yeah.
Tired or not yet? Any question? Irregular? For irregular heart rate or for regular? For irregular. For irregular, we know that RR is changing. So it could be short then long, short then long. It's short. If I take this R to R, for example, the rate is 100. And the other R to R, the rate is 60. So what is the rate? Is it 60 or 100? If I take also these 2 beats, it's different from other few beats. So what we used to do is just take 10 seconds, see how many QRS complexes in that 10 seconds. This is how many beats in 10 seconds. I want a 1 minute, so I multiply by 6. Because this is only 10 seconds, I want 60 seconds. No, don't average. Because in this case, for example, if in 10 seconds I have 10 beats, So in 1 minute, what do you expect to have?
60.
60, right? Because 10 by 60 is 60 beats per minute. If in 10 seconds I have 100 beats there, so I multiply it by 6, and it will give me how many in the minute. This is again, just remember 300 by RR intervals in large squares, or 1500 in RR in small squares will give you the heart rate. For regular rhythm, of course. Oh. To know the rhythm, whether it's sinus or not sinus, it depends on, number one, the rate itself. What is the normal heart rate? 60 to 100 beats per minute, and the resting state without exercise, without excessive physical activity is between 60 to 100. Less than 60, we call it bradycardia. Above 100, tachycardia. So first part, we look to the rate. Is it within the normal range, or in the tachycardia area, or in the bradycardia? Second, look for regularity. Is it regular or irregular? Because if it is irregular, usually you have three common rhythms that we can think about: atrial fibrillation, atrial flutter with variable conduction, multifocal atrial tachycardias, or premature beats, whether ventricle or atrial. These are other than that, usually it is regular. Whether it's ventricular tachycardia, atrial tachycardia, or others, usually it is regular. So if it is irregular, we limit our diagnoses into few possibilities. The third is relationship between the P wave and the QRS complexes. So if P wave followed by QRS complex, and the P wave morphology is sinus rhythm, we are dealing with sinus rhythm. And if it is tachycardia, it is sinus tachycardia. If it is brady, it's sinus bradycardia. So these three, if you start with them, it will give you the rhythm. And we'll show examples. Now, when you come to the QRS complex axis, or cardiac axis, what does it mean? What's the meaning of axis? Axis is the average direction of wave of depolarization. So remember, the heart is like this. Activity goes from up, down. It's spread actually in three-dimensional, so it goes everywhere. But what is the main vector of activation? The one that is going towards the lead 2, which is 60 degrees, right? So activity of the heart spreads everywhere. However, the net of that activation is our cardiac axis or vector, and this is the one we look forward to see if the axis is normal or whether we have right axis or left axis deviation. So average direction of the heart's electrical activity is the axis. Remember, if you have a waterfall, so if it goes this way to there, everybody will see the direction of the water is this side, right? However, we know if you are beside it, you can see some water actually flows to your side. It goes everywhere around, but the main thing is coming from up down, but actually it spreads every direction. So the same for cardiac activity. Yes, it spreads everywhere, but where is the main thing is actually the cardiac vector. Okay. Now, what is the normal axis for the heart? So the heart is like this. Activity goes this way. This is the normal. So most of the time is towards 60 degrees. This is the normal. But like anything in life, there is some variations. So when we take normal people, it was found that between minus 30 to 90 degree is the normal axis. So because actually depends if somebody is obese, underweight, tall, thin. So there is still variations. It can change the shape of the heart in the chest. So for example, if somebody is tall and thin, the heart will be like this, right? More vertical. So we expect to have some right axis deviation. If somebody is obese and the fat is pushing the heart to the left, you have left axis deviation, right? So within minus 30 to 90, this is the normal axis of the heart. When it is between minus 30 to minus 90, this is towards the left side of the patient. So this is left axis deviation. If it is between 90 and 180, this is right axis deviation. The area here in between, which is 180 to minus 90, called extreme axis. Could be extreme right or extreme left. We cannot tell. And this is most of the time we see it with ventricular tachycardia when the activation is totally abnormal. And once we see somebody axis in this area, we think of ventricular tachycardia because it's not physiological at all. It cannot happen even with just minor changes like with myocardial infarction or other things that can cause left axis or right axis deviation. Then, how to determine the axis? Very simple and easy. Look to lead one. And let me go back again. So if let's say the axis is within this range. So lead one will be positive or negative? Positive. AVF positive or negative? It is positive. Right, excellent. Right. So in normal axis, you expect lead one and AVF to be positive. If the axis here in the left side, lead one will be positive or negative? This is the positive side, so this is positive, right? AVF positive or negative? Remember, this is the positive and this is the negative part, so negative. So they are moving away from each other. So if I see QRS complex, and lead 1 positive, and in AVF is negative, they are, I think, okay, let's take the left axis deviation. Is it enough? No. Why? We have to look lead 2 in this case. For left axis to confirm it, we look to lead 2. If lead 2 is negative, this confirms that this is left axis deviation, right? Because in this area, lead 1 is positive, lead 2 and AVF is negative. What if lead 2 is positive? It cannot be in this area. It must be around this area between 0 to minus 30. So still within the normal range. So for left axis deviation, we look to lead 1, AVF. If lead 1 is positive, AVF is negative, they are the opposite direction. I look to lead 2. Lead 2 is negative, this is left axis deviation. Lead 2 is positive, no, this is still within the normal range, right? For right axis deviation, lead 1 positive or negative? Because this is the negative side of lead 1, so it is negative. AVF positive or negative? Positive. So they are facing each other. They are agreeing with each other. In this case, you don't need to look for lead 2. When they are facing each other, lead 1 is negative, AVR is positive. We say we are having right axis deviation. We don't need to look for lead 2. But for left axis, you have to look lead 2 for confirmation. Clear? So both positive, normal axis. Lead 1 positive, AVF is negative. Likely left axis look to lead 2. Lead 2 is negative, confirms left axis deviation. Lead 2 is positive, no, this is still within the normal range. For this right axis deviation, it will be negative in lead 1 and positive in AVF. Clear? If both negative, we cannot tell where is the axis. It is that one, remember that quarter here, both negative. In this area, we call it undetermined axis. It could be extreme right or extreme left, we don't know. Now, what can cause, this is actually the same explanation, so I will just skip that one. What can cause left axis deviation? Why we are interested to know axis deviation? Because it can tell you there may be some abnormality. So one axis should look to the left, for example. Sorry, what's that? Hypertrophy? Yeah, left ventricular hypertrophy. So yeah, if the left ventricle is hypertrophied, the vector will shift to the left, of course, because more mass in the left side and more activity going to the left side. So left ventricular hypertrophy is an example. Left bundle branch block also. Activity is going to the end. What's that, sorry? Not the diaphragm, but actually it is obesity or thin people. That when I mentioned earlier. So if somebody is obese, it can push the diaphragm, push the heart. So the heart is pushed to the left side, the axis will move also to the left side. So obesity is one of the causes too. If somebody has inferior myocardial infarction, so the inferior surface, we lost the activity in this one. So main activity is in the anterior and lateral wall, so the axis will go to back, right? Opposite to it is the right axis. Right axis deviation, what could be a cause of right axis deviation? Right ventricular hypertrophy, right bundle branch block, so there are things that happen on the right side. Core pulmonary, when there is pulmonary disease affecting the right side of the heart, more muscle in the right side, so more activity going to the right side, we have right axis deviation. So these are examples of them, and these are examples. Wolff-Parkinson-White syndrome, this is an abnormal connection between atrium and the ventricle, called bundle of Kerr. If it is in the right side, cause right axis deviation. If it's in the left side, cause left axis deviation. So it depends on the location. Remember that right axis deviation can be normal in young people. So we don't worry. Left axis usually is not normal, but right axis can happen in young people. Okay, any question? So we are okay? And by that, actually, I finished. Thank you very much. If you have any questions, we can discuss.